Okay, this lesson is about differentiable functions or derivatives of functions. And it's based on continuity, first of all. And so you can take the derivative as long as a function is continuous. That's what this first one says. So remember, continuous, as far as the definition of continuity goes, says that there are, the limit exists at c, and that the value exists at c, and the value and the limit are the same. So there's no breaks, no jumps, no holes, no asymptotes. So any place that would happen, you're not going to be able to take the derivative. Also, on number 2 here, it says that if you have a sharp turn in your function, then you can't take the derivative at that sharp turn. So in this picture, where x equals 5, we would not be able to take the derivative. Now, this makes sense. When you're looking at this function, we know the derivative is the slope, and the slope of this left side would be -1. The slope of the right side would be +1. And so the slopes coming in from the left and the right are not the same. You can't take the derivative anytime there is a sharp turn. Sometimes two curves can come together. For example, like a curve and a line for a piecewise function. Still the same thing. This is called a cusp whenever they come together like that. That anytime there's a sharp turn like that, you're not going to be able to take the derivative there. Then also, visually, if you can zoom in on that space, and the more you zoom in, the more it looks like a straight line, then you would be able to take the derivative. If you keep zooming in, but it still doesn't change, it still has that sharp turn, then you would not be able to take the derivative. Now we're going to talk about, that's kind of a not a very mathematical way to talk about that. So we are going to talk about how you would know for sure whether or not it's going to come together and make a smooth line at that point or not when it's a piecewise function. So we have one of those in our notes on the back. But for the most part, you can't take the derivative if you have any kind of discontinuity, a jump, a hole, an asymptote, or you can't take the derivative at a sharp turn. Third, we can't take the derivative where there's a vertical tangent. So at 0 right here, we know that as we get closer and closer and closer to 0, my lines begin to get closer and closer and closer to a vertical line. And so because there is a vertical tangent, and a vertical tangent is an undefined slope, and we're finding slopes when we find derivative, then you would not be able to take the derivative where that would happen, where you would have a vertical tangent, because there's not a slope for a vertical tangent. So this is what I was talking about for your homework. I told you it was going to be kind of an easy one. So a lot of your homework problems are like this first example here. It says that it wants us to state the reason and the numbers at which f is not differentiable. So we can start over here at -1. At x equals -1, it's not differentiable because there is a sharp turn or a cusp for the two curves come together. Then right here, we have a jump. So at x equals 2, it's not differentiable because it is discontinuous. And then we come over here to 1, 2, 3, 4, 5, 6. At 6, we have another cusp. So it is not differentiable. And then it looks like right in here, they've created a place where there might be a vertical tangent. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So at x equals 11, it looks like there's a vertical tangent. So all of those would be spots where this function is not differentiable. You couldn't take the derivative. All right, so like I said, some of them very simple. Just look at the graph and then state where it's not differentiable and why. Now let's look at this second example. And this is what I was talking about. This is a piecewise function. And we know that if a piecewise function comes together, let me show you what I'm talking about, like with a line and then a curve like this, then if they came together like that, even though the graph would be continuous, that doesn't mean that we could take the derivative because it's like a cusp. But if my graph came together with a line and then maybe right here it turned into a parabola, maybe you would be able to take the derivative there. Because if we zoom in enough, it probably would look like a straight line. So we can't just look at the piecewise function and determine whether or not, unless we graphically can tell that it's going to come together at a cusp, we can't just first be certain that we can't take the derivative. So, all right, so first of all, I just want us to take a look at these two graphs and where they come together at 2. So let's just look real quick. There's our parabola. Here's our line, maybe. There it is. And so at 2, where they come together, it makes it pretty seamless right there because we're supposed to be looking at the parabola to the left of 2 and the line to the right of 2. So we'd be coming down this line and then we'd join into the parabola. And so very, very likely that we might be able to take the derivative. So here's what we're going to do so that we can be mathematically sure. We're going to take the derivative from the left. And so the left side is this side, right, to the left of 2. So we're going to take the derivative at 2 using this function. So it's at a point, so it'd be the limit as x approaches 2 coming from the left of our function minus our function at 2. So 2 squared would be 4 plus 1 is 5, so minus 5 over x minus 2. And so we have the limit as x approaches 2 from the left of x squared minus 4 over x minus 2. And so we can factor that out. Have x plus 2, x minus 2 over x minus 2. X minus 2 divide out. So now I can plug in my 2 and I get 2 plus 2 is 4. So the derivative from the left is 4. Now we're going to take the derivative from the right. So again, at 2, but from the right-hand side, we're going to use the other function. So we're going to have the limit as x approaches 2 from the right of 4x minus 3 minus, and then plug in our 2. So this would be 8 minus 3 is 5 over x minus 2. So I get the limit as x approaches 2 from the right of 4x minus 8 over x minus 2. And I can factor out a 2. So I have the limit as x approaches 2 from the right of, oh wait, yeah, I can factor out a 4. X minus 2 over x minus 2. So I just get 4. And so since both of those one-sided limits give me the same derivative or the same answer, then the left-hand and the right-hand derivatives are the same or equal, and that makes it differentiable at 2. So if you're ever unsure about whether or not it's coming together as a cusp on a piecewise function or whether it's a smooth transition from one function to the other, you can take the derivative from the left and the right to determine that. So let me write that down. The left and right derivatives for the one-sided limits are equal. So therefore, we have a differentiable function at x equals 2. Now, if that had, oh, you can see all that. So if you had taken the limit from the left and from the right and they don't come out the same, then the one-sided limits are different, and therefore the slope coming in from the left and the right is not the same. So you wouldn't have a derivative at that point. It would be a cusp. So this is how we will determine if it's not easily determined just by looking at the graph.